Okay, here's an example of two dependent means. Now, how do we recognize when something is dependent? There are kind of really two categories. The most common dependent mean example will be when something is tested twice. So think of it as test retest. So you could give a bunch of students a pre-test and a post-test. Then obviously those are paired up data. You could weigh a bunch of people, and then put them on a diet and then weigh them again. So you have kind of pre and post, right? You could measure arm strength and then do something, some sort of stretching activity or some sort of intervention, and then measure arm strength again. So anytime you have a pre and post measurement, then you automatically have dependent means, dependent data. The second more subtle kind of example of dependent is when you have two measurements that didn't come from the same thing, but there's a logical connection between the two. And I've talked about this in other videos where you would have like measurements on two spouses or measurements on two siblings, measurement on two arms, right? Trying to decide if your left and right arm are different. We've seen examples where they looked at the president and then the vice president. So like IQs of presidents and vice presidents, so there's a relation between those. And so if there's a natural matching, a natural pairing between the two, then you can consider, you don't have to, but you can consider doing a dependent or paired t-test. And it's a more powerful tool when you can pair them up. The other telltale sign is if your two sets have the same number, right, the same amount, so the ends are the same. So in this case, they're both 5. Then you can think that they might be paired. If those two sets had different amounts, then they're automatically can't be paired. So it's really easy to recognize when something isn't paired data, and that's if they have two different sample sizes. Okay, so if we were given this on a test and we weren't told that it was from a chapter on dependent samples, we would hopefully recognize it because it's talking about measuring two arms, and you would think, okay, well, there's a logical relationship between those two, and therefore I'm going to use the much easier, much simpler formula for the t-test that just looks at the differences. So we need to calculate all of these differences, right? So the difference between these two and so on and so forth. And then d bar is just the mean of those differences. And then we're going to subtract mu sub d. And mu sub d, remember, is just our hypothesized difference. So in this case, the claim, right, we're looking to test for a difference between the measurements of the two arms. So isn't the null going to be the same? So that's going to be just 0. So we're basically just going to have the average of the differences divided by, this is S sub d. I'm sorry, it looks like an A, but that's S sub d, which is just the standard deviation of the differences. So after we get these 5 different scores, we're going to have to calculate the mean and standard deviation of them, and then we divide that by the square root of n. So you can see that it's really getting right back to that very simple z-score formula of x minus the mean all over the standard deviation divided by the square root of n when we were using the normal curve to figure out probabilities of samples of things, right? And here we have a sample of 5 because we have 5 differences. So it's really the exact same formula, only we're doing it for t's instead of z's. Okay, so you could calculate all these things, all the differences by hand, then you could calculate the mean and standard deviation by hand, or you could let technology do the work for you. Now, if you're doing your calculator, you put one set in list 1 and the other set in list 2. It does not matter which one goes in list 1 and list 2, just as long as you keep them in order. And what I mean by in order is you're not putting them in smallest to biggest. You're putting them in the order in which they appear because they need to be matched up, right? 143 has to go with 169. The second 143 has to go with 172, and so on and so forth. Now, you don't need those numbers, you only need their differences. So if you calculated those 5 differences by hand, then by all means, just put those 5 differences into a list because that's what you ultimately need. But if you want technology to do all that for you, just arrow up until list 3 is highlighted. And now all you have to do is define list 3 as, we hit second, number 1, because that brings list 1. You see down here in the bottom, it says list 3 equals list 1 minus, and then do it again for list 2. So second 2 gives us list 2. Hit enter, and it now defines list 3 as list 1 minus list 2, and it does all the math for you. It calculates all the differences for you. Pretty cool trick if you didn't know how to do that already. Now that we have what we need in list 3, we're just doing a simple t-test on list 3. So we're actually just going to quit out of this and go stat test t-test. We do it on data. We come down here, we put in what the hypothesized, right, mu sub 0 is, and we're leaving that at 0 because we're hypothesizing that there's no difference between the two. And then we have to tell it where our list is, and in this case, second 3 gives us list 3. Frequency, we don't need to deal with that, just leave it at 1. You would do frequency if you had weighted means. So you would put the weights and you would tell it where those weights were. That would be a different list, right? And this we're testing for a difference. So our alternative is just that they're the same or different. Calculate. There's our T, there's our P. It's everything we need to know, very quick and simple. If you wanted to do it in StatCrunch, it's even easier. And the reason why it's easier in StatCrunch, in my opinion, is because you can click on these little boxes right here and open your data straight in StatCrunch, and you don't have to worry about typing the numbers in. They just appear in the table in 2 columns, and you can do the math right on those numbers, right? So you don't have to worry about maybe mistyping something into your calculator, putting in 134 instead of 143, those kind of simple, easy mistakes. Now that all of our numbers are in, we can go stat, tstats, paired, right? Because we're doing paired data. We select where the stuff is, right? So there's my first sample is the right arm, second sample is left arm. If we want to, we can save the differences in the table in case we want to do other work with them. I always say that's a good idea to do that because you never know what other kind of calculations you're going to need to do. We're running a hypothesis test, right, where the null is that the differences, right, the mean mu of sub d, the mean of the differences is 0, and the alternative is that they're not. We compute, and we see we get the exact same thing that we got out of the calculator. And if we move this down, we can see that we have all of our differences right here that we also had in the calculator in case we need to do other things with it later. Okay, so working with paired data is even easier than independent data because it really just becomes a simple t-test. Hope this helps.